Concavity requires us to find the second derivative. Recall that the first derivative is 4x plus 1 over 3x to the, where'd it go? 2/3. What I would recommend doing is maybe putting this into a product rule again. So I would rewrite this as 4/3 x plus 1 and then x to the negative 2/3. Okay, so the second derivative. We're going to do a product rule now. We're going to leave the first piece alone, multiply by the derivative of the second piece, which is that x to the negative 2/3. Plus, you're going to leave that second piece alone, multiply by the derivative of the first piece. All right, so we got 4/3 x plus 1, and then the derivative of this. That's going to be a power rule. So bring the negative 2/3 down, x, and then there'll be negative 5/3. We're going to leave the x to the negative 2/3 alone, and then differentiate this. Now this, that's the same thing as 4/3 x plus 4/3. The derivative of that is just 4/3. Okay, now we just have to factor. Notice that, actually let's clean this up a little bit. We got negative 8 over 9. Let's do x to the negative 5/3 x plus 1 plus 4/3 x to the negative 2/3. Alright, they both have a 4/3. So I'm going to pull out a 4/3. What else do they have? This x to the negative, now it has to be the smaller one, so between negative 5/3 and negative 2/3, it's negative 5/3. Now what's left over? Well, in this case, it's going to be a negative 2/3 x plus 1. And then over here, I pulled out the 4/3 and the x to the negative, actually I pulled out an x to the negative 5/3. So that means there is some x left over, and it's actually just going to be 1. Because if you were to add these two together, negative 5/3 plus 1 is negative 2/3. So we just have to clean that up. 4/3 x to the negative 5/3. That's going to be negative 2/3 x plus, oops, sorry, that'll be a minus 2/3. There we go. Plus x, almost done. So 4/3 x to the negative 5/3. And then we're going to get negative 2/3 x plus x. That's a positive 1/3. And then x, 1/3 x, minus 2/3. Alright, so here is our second derivative. Alright, next step would be, oh, and then if you actually clean that up a little bit, sorry, we can factor out actually a 1/3 here. And if you factor out a 1/3, you're going to get 4, and then you pull out a third, you're going to get 9 x to the negative 5/3. And then if you pulled out a 1/3, that's just going to be an x minus 2. Alright, so that's how we get this right here. All they did was we brought the x to the 5/3 down to the bottom. So now what we're going to do is set the second derivative equal to 0, and when the second derivative does not exist, we're going to answer those two questions. Now when the second derivative equals 0, that would just be when the numerator equals 0. You do not have to set the denominator equal to 0 in this case. However, in this case, we do, because that's exactly when the second derivative doesn't exist, is when the denominator equals 0. Solving these, we get x equals 2, and over here, we get x equals 0. So we have two basically critical values to the second derivative is 2 and 0. So let's go ahead and plot that on the number line. So we have 0 and 2. We're going to pick a number from each region, just like we did with the first derivative, plug it into the second derivative to figure out our concavity. So I'm going to pick, say, -1. I'm going to pick 1 and say 3. Those should work. We're going to plug those into the second derivative. So I'm just going to set that up here. I just need to figure out what those are. Now again, recall that the second derivative is 4x minus 2 over 9x to the 5/3. So when we plug negative 1 in, we're going to get 1 minus 2 over 9, negative 1 to the 5/3. And that's going to give us positive 1.33 repeating, which is greater than 0, which means we are concave up. So I'm going to put a concave up here. Now if you plug in 1, I'm not going to write it out again, I'll just tell you what it is. You get a negative 0.444 repeating, which is negative, which means we are concave down in this region. Finally, when you plug in 3 into the, well, I'm using a calculator, we get 0.0712. That is greater than 0, and so we are concave up again. So with this, we want the intervals of concavity. We are concave up from negative infinity to 0, and then again from 2 to infinity. We are concave down, 0 to 2. Do we have any inflection points? Inflection points would be when we change concavity. And you have to be a point on the graph. Remember that you actually have to be able to be plugged into the original function, because you have to be a point. So this was the original function. Now 0, we change concavity at 0. So when we plug 0 back into the function, we've done this a few times already, we get 0. And our other inflection point is at 2, because if I plug 2 into this, I get 7.56. I trust that you can check that out. I now have all the information I need to sketch the graph. So here's a summary of everything we know. Let's pull out a graph and let's start doing this. We have intercepts at -4 and at the origin 0. We have no local max, but we do have a local min at -1, 3. What else? We have inflection points at 0, 0, and 2. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. So about right there. Is that it? Do we know everything else? All right, so we are, what's happening over here? We are decreasing from negative infinity to -1. So that means we are going down like this. And then from -1 to infinity, we are going up. So we're going to have some sort of weird looking V-shaped thing, but we need to use now the concavity to connect these. So from negative infinity to 0, we are concave up, which means this whole thing right here, all of this is concave up. So let me change colors. So we're coming down, so decreasing, concave up, we hit our local min, and we're up here. Now what's actually happening at the origin? Now it's not listed here, but remember a critical value was x equals 0. Now why was that? It's because f prime of 0 did not exist. Now if something does not exist, it means it could have been a corner, it could have been a vertical tangent line. In fact, that was actually what was happening. It was a vertical tangent line. So our function goes vertical right here. Now notice that after 0, we are still increasing because we are increasing from -1 to infinity. So we are increasing for the rest of the time. But at 0, we then switch to concave down. So between 0 and 2, we are now concave down. So we look something like that. After 2, we go back to concave up. Still increasing though, because we are still on this interval. And so we go something like that. So this is my little concave up here. This is my little concave down. And all of this is concave up. And so here's the graph to the function x to the 1/3, x plus 4.